Good morning. We are going to be working on lesson 3.2 today. And you're going to want to make sure that you follow along. You have my Stat Lab open with StatCrunch available. There are some data sets that I will refer to that are in StatCrunch under my data and our class data today. And also have your course back out and open because I'm going to fill in your course back along with the YouTube video. So we're working on 3.2. And I'm going to share my screen here. So right here we are. It says, thinking back to 3.1, we talked about the three measures of center, and we said the three measures of center are the mean, the median, and the mode. But center is not the only thing that we look at when we look at a data set. Measures of dispersion are just as important. So dispersion is defined as sometimes called variability, scatter, or spread. We're going to use the term spread quite a bit. So dispersion is the extent to which a distribution is stretched or squeezed. The four measures of statistical dispersion we are going to talk about are range, variance, standard deviation, and interquartile. Dispersion is contrasted with location of average, such as the mean. So the mean and the mu are those symbols, but we're going to talk about dispersion. And together they are most used as properties of location. So remember that the mean and the mu are directed and a characteristic of our center. But now we're going to talk about our dispersion. So you can see below that we have two data sets here. And they're in different bins, just like our histogram. And you can see that this group here has what we're going to reference as that standard deviation. This SD is 10. It's very small. Where the mean is centered at 100, you can see that the red data set is all very centered and piled up high. These are all observations here, 350 observations in this one piece here that are all centered around the mean. But the blue data set is very spread out. Its center is also at 100, but its variation is much bigger. They have values that are down here under 0, and they have values in the bins up here in 210, 220, and 230. And so this much higher standard deviation, you can see that's measured at 50. So I'm going to have you turn in your StatCrunch and pull up the data set that says CP 3.2 exam data. And there's going to be one column that is the algebra exam and one that's the stats exam. And when we look at that data, the first thing we're going to look at, the first measure of dispersion is the range. The range is calculated as the maximum minus the min. So you'll notice that some texts will write it in words, so 2 to 19, while others will give it as a number. For example, 19 minus 2 is 17. So we're going to use this. Okay, we're going to actually find the subtraction, the difference between the max and the min. So before we go to StatCrunch, we're going to look at the range for our data set here. We have a sample of, and notice we're going to make sure we notice that this is a sample of algebra students, and they took an exam, and here are their scores. And then there's another class that took a stats exam, and here are their scores. And the mean for the algebra students is 74, and the range for the algebra students is 100 is the max, minus 60 is the min, so the range is 40. Now, the mean for the stats exam, we're going to go to StatCrunch and calculate that. So let's go there. And here we are. So we have the algebra exam and the stats exam, and we want to go to summary statistics, just like we did in 3.1, to columns, and we're choosing statistics. because we want to know the average of that class. So let's just go down and hit compute. And the only thing that we're looking at right now is the mean. The mean is 74. So we can fill that in. They have the same mean as the algebra students, but their range is going to be the max minus the min, which looks like it's also 100 minus 60, which is 40. So on the surface, they appear to be very similar. In fact, almost identical, right? Their mean is, both have a mean of 74 and both have a range of 40. But if you look at the dot plot below, here are the algebra students, their actual scores. And here are the statistics students. And I'm going to ask you to make a statement on your paper. Which class would you rather be in as a student and why? And letter D says, how useful are the mean and range for comparing these data sets? So I'd like you to pause the recording and think about this for just a minute. So welcome back. Hopefully you've had a few minutes to think about which class would you rather be a student in? I would rather be a student in algebra class. And that's because if I randomly got one of these scores, I'm most likely to be in the center somewhere where that mean is at 74. I might on accident, or not on accident, but I might randomly get the score of 60, or I might randomly get the score of 100. But I know that I'm most likely to score around the center. I am most likely to score around 74. And you can see here that the statistics students are very much spread out. In fact, no one even scored a 74 in that class. There was a couple 76s, a 76 and a 77, and then much lower, and then just that one student that had 100. So it says, how useful are the mean and the range for comparing these data sets? Not useful at all. Because until we looked at the actual dot plot, we thought they were almost identical. So let's flip the page here. So we need to decide just how far off are those statistics students from the center. So it says we need a more sophisticated number or two that will measure the average amount of deviation from the mean. That's what the standard deviation and variance will do. But first, let's explore where they come from. So we're going to consider the statistics students, and I'm going to mark the 74 as the mean. And so you can see that visually, you can see how these students are separated from the mean. Okay, well, deviation is going to be calculated by the measure of taking. So let's write this down. Deviation is equal to the observation and subtracting the mean. Okay, so for this first student, their observation was 60, and we're going to subtract the mean, and we get a negative 14. So it's always important that you're consistent. Sometimes you'll get a negative. Let's think about what those might mean. The next student, when we subtract the mean from the observation, they scored above the mean, right? So I'm just going to fill in each of these. Okay. So it says compute the deviation from the mean for each of the students. Place the values in the middle column, which we did. Here's our deviations. What information does the sign of a deviation convey? So a negative deviation means the student scored below the mean. So negative means that the observation was below the mean. A positive deviation is the student scored above the mean. Okay. But we want to find the average deviation. And so we know already that an average is when we add up the values and divide by the number of observations. So we want to find average deviation because that would tell us about how far all the scores were from the mean. What is the problem with adding the deviations and dividing by how many there are? What can we do mathematically to fix this? So we would add all the deviations. So go ahead and do that. And that's what this symbol is here. It is to sum. So when we do that, we get 0. I'm going to write that down here at the bottom. Our sum equals 0. So when 0 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students, it appears on our value that we have on average 0 deviation. But we know that's not true because we can confirm that the first and third and fourth students were all way below the mean, and the second student and some of the others were way above the mean. It just happened to be that the students scored just above and just below enough that when you added their deviations together, we got 0. So that's not going to give us anything that we need that's relative. Okay. What we could do though is we could say, what if we took that deviation and we were to square that deviation? Okay. What squaring does is it inflates the number. It makes it squared big, right? We take the value and multiply by itself. But what it does is it in turn makes all of them to be a positive value. So if we do that, here are the values that we get. Okay. Now, because we have all positive values, if we were to take the average of these, we would get a positive value. So let's go flip the page. I want to reassure you, you are never going to have to do this by hand in our class, but I want you to see why we're building up to what we are, because we can't simply take their deviations and average them, because sometimes circumstantially we would get 0. So we're going to take the deviations and we're going to square those deviations. And when we square those deviations, that's right here, we're going to add up those and divide by n. So we're taking the average of the squared deviations. Okay. This is called population variance. Now, you'll see that that's because we use mu, right? Our population mean. And down here, you'll see the sample variance is because we use the sample mean. And remember, when we calculate the mean, they're calculated the exact same way, whether it's population or sample. But because when we have a sample, we are estimating the mean, right? We're using the sample. We don't know the population value. So we're going to subtract 1 from our sample size down below, the n-1, to compensate for that. Okay. So our population variance has this symbol here. It's called sigma. And to go back to our original units, we have to take the square root of that, because remember, we square the deviations over here. Okay, so this has no units. And this has original units. Okay, and this is population because it has the sigma. Remember, population symbols are always Greek symbols. Mu for the mean and sigma for the standard deviation and variation, variance, and then just letters for the sample. So again, the sample variance has no units. But when we take the square roots and get the standard deviation, we have original units. Okay. So we're going to use StatCrunch to find these. I'm going to show you that here in just a minute. And then there's also a way you can do it in a graphing calculator if you really want to use it, but I highly recommend using StatCrunch. In the back of your course pack, there are instructions on how to use your graphing calculator, and I can always assist with that as well. But I want to show you the relationship between variance and standard deviation. Okay. So if we take the standard deviation and square it, we get the variance. It doesn't matter which symbol we start out with. Okay. So S squared, we get S squared. Or sigma squared, we get sigma squared. We get variance. Okay. If you have variance and you want to go to the standard deviation, then the standard deviation is equal to the square root of the variance. Remember, squares and square roots undo each other. Just like 12 squared is 144, and the square root of 144 is 12. So this standard deviation will be the square root of this variance for the sample. This standard deviation will be the square root of this variance of the population. So let's go back to StatCrunch so I can show you the differences here. So we took, I'm going to start over here. Let's go back to, if you flip your page to page 86 in your course pack, this will help us. It says, but what do these numbers have to do with the data? How do we interpret the standard deviation? So I says the algebra class has a standard deviation of 10.176 points. And the variance, if you square 10.176, is 103.56. I'm going to show you this because this always seems to be a little bit of a confusing point for students. So the standard deviation from the algebra class, if we were to square that value, we get 103.56. Okay. We will never calculate this by hand. It will always be using StatCrunch. But we're going to go to StatCrunch and we're going to calculate for the statistics class, the standard deviation and the variance. Okay. And they're samples, so that I want to make sure I point that out because they're samples, sample data. So we're going to statistics and summary stats and columns, and we're choosing statistics. And notice this is what we've chosen so far. Okay. The mean, the variance, and the standard deviation. Now, over here in the gray, I could have chosen unadjusted variance and unadjusted standard deviation. I'm going to do that for now. I'm going to add those by clicking my control button and my mouse at the same time. I can add those over here. So I added them over here. And now I can hit compute. Okay. So the unadjusted variance and unadjusted standard deviations when we have population data. When we adjust it, it's because we're adjusting for the sample, the fact that it's a sample and it's not every data value that we want to collect. Okay. So for us, because we have a sample, we want to use the regular variance and standard deviation they give us right here. Okay. So that standard deviation is 13.968. 13.968. And if we square 13.968, we should get 195. And I got 0.105. Now that's because I squared a rounded value. if you square this raw value, the way the calculator did that for us right here, then you're going to get this variance of 195.111. And that's okay. They're just a tinge off. That's all right. Okay. So let's just go back to, remember, I want you to make a comment on your paper. Unadjusted is for the sample. I'm sorry, unadjusted is for the population. Regular variance and standard deviations from the sample. Okay. Let's write that on our paper together. Unadjusted is for the population. Okay. And they wanted us to mark these. So there's our 74. And you can see that the standard deviation for the statistics class is much bigger than the standard deviation for the algebra class. Okay. So this gray boxes right here on page 86 are very, very, very important and highly recommended that you add them to your note sheets for the midterm and the final, because we are going to be talking about these for a very long time this semester. Okay. So it says the larger standard deviation and or variance goes to the data set with more spread or more dispersed. Variance is, there is not a practical interpretation of variance. Instead, it's a measure that's used in later chapters. So we're going to talk about variance, but we're only really going to interpret the standard deviation. Standard deviation can be thought of as roughly the give or take from the mean in a symmetric data set. In other words, most data falls within a standard deviation or two, and we're going to learn about that here in a few pages. So here is a script. You are always going to use this. When I said just interpret the mean and standard deviation, I'm going to be asking you this on worksheets, in the course pack, on the midterm, all the way down to the very last day of the semester. So it's important that you're following this right here. We expect, okay, and then what's in brackets, we're going to change about our context. So we expect the data value, whatever it is, variable, to be blank, which is going to be the mean. We're going to put the mean here, give or take the standard deviation. Okay, and we're using the words give or take. We're not going to say the mean is this and the standard deviation is that. That's when I say interpret, you're going to be marked wrong for that. So I want to make sure that's very clear. What might we consider an unusual value? Okay, so you might have already been thinking, wow, these people that scored 100 up here, they seem pretty unusual because most of the data is falling in this area. So to be considered unusual, anything that is beyond 2 standard deviations away from the mean is considered unusual. That means if they could be 2 standard deviations above the mean, they scored higher than the average person in the class, or they could be 2 standard deviations below the mean. They scored below the average person in the class. They would be considered unusual, okay? Now, any values within less than 5% probability are also considered unusual. We are not even going to worry about that until chapter 5. So don't worry about that statement, but we're giving you both ways to think of unusualness now. Okay, so recall that the mean for the data set was 74. Interpret the mean and standard deviation in the context of the situation. Okay, so we are going to follow this right here. We expect we'll go with the statistics student. The statistics students to score, and then I'm going to put the mean, which is 74, comma, give or take, and I'm going to write down this standard deviation, 13.968, 13.968 points. So it's critical that you have units as well. Be sure to include units where given. Did the statistics course have any unusual values? So if my mean plus 2 standard deviations, what would I get? That would be 74 plus 2 times 13.968 is 2 times 13.968 is 27.936. That would be, somebody would have had to score 101.936. Okay, didn't have anybody score higher than 100, right? Or it could be the mean minus 2 standard deviations. So 74 minus 27.936 would be, did anybody score lower than a 46.064? No, our lowest score was a 60. So it's no. That's how we can tell if there's something unusual or not. Okay. So just for the fun of it, let's go back to our PET data from lesson 3.1. And we had the mean and standard deviation and variance. So let's go back to backbench momentarily here. And I'm going back to my PET data here. So you'll want to get out the project student surveys. You can just follow along with me if you'd like. So I'm going to go and do summary statistics by columns. And I'm going to scroll down to how many pets do you have? And because we decided that ours was a sample, I said you could really kind of choose it either way, but I chose mine as a sample, but I'm just going to run it just as it is and hit compute. And this is without the person that had those 127 pets with the tarantulas. Remember that? They had a mean of 3.079. And we're going to write down their variance and standard deviation. So the standard deviation S, we're going to use that symbol because it's a sample. So S is equal to 2.749. And the variance is S squared is equal to 7.558. And we said their statistics, because it's from a sample, we don't have every student data at Jackson College. So we're filling in page 87, A and B. Okay, so this is interpret the mean and standard deviation in the context of the situation. So we expect the average student to have, what is it, 3.079 pets, give or take 2.749 pets. Remember the mean was 3.079, I believe. Did we have any class members with an unusual number of pets? So what we'd have to do is take the mean and add 2 of these standard deviations to see that. So 3.079 plus or minus, we can do it both ways. 2.749. And then I'm going to use my TI-84 because for these situations, it is nice and handy because it's much quicker. Because I can do this in one step. 3.079 plus 2 times 2.749. So did we have anybody with 8.577 pets? We did. We had some people that had 10 plus pets, right? And then the less than, so we could arrow, if you do have a graphing calculator, you can arrow up. Oops. No. Okay, I'm just going to clear that out and start over. 3.079 minus 2 times 2.749. And we did not have anybody with negative 2.419 pets, so that's not even an option. But we did have some people that had more than 10 pets. Now it says, with the 127 pet student, calculate the mean, standard deviation, and variance. And what do you notice? So let's add that student back in here. And we said we are going to go back in and give somebody 127 pets. And we're going to go to stat and summary stats by column. How many pets do you have? Compute. And the mean went up, right? So let's just write this down. The mean, the X bar is 5.016. We found that in 3.1. The standard deviation is 15.728. And the variance is 247.381. So the standard deviation increased dramatically. Share my paper with you. So the mean increased from 3 to 5, but the standard deviation increased, right? From 2.749 to 15.728. So pretty dramatic increase there. Okay. So a few final notes about the standard deviation and variance. Variance is a measure of how spread out an entire data set is. We have our population symbol, sigma squared, and we have our sample symbol, S squared. The standard deviation is a more practical measure of how spread out an entire data set is than variance. In other words, the standard deviation represents the average distance the values in a data set are from the mean. It has units. This is the one we're going to really use. It has units. Okay, and that symbol is sigma, and that sample symbol is S. Some important notes. Variance and standard deviation are always non-negative. Okay, they're always positive values. Variance and standard deviation are not resistant to skewing or outliers. You can see that, right? That when we have outliers like the student with 127 pets, they really skewed our data set. Standard deviation, both sigma and S have the same units as the original data. Variance has our original data unit squared, and population values are sigma and sigma squared are called unadjusted in computer outputs. Okay, so we mentioned that earlier. Example 4 says, is it possible for a list of numbers to have a mean of 74 but a standard deviation of 0? If so, explain how with an example. If not, explain why not. I want you to think about that. Okay. The only way, yes, is only if all data points are 74. the same as the mean. Right? If they are any different than the mean, then you're going to have some variation. So the only way for that standard deviation to be 0 is if every data point is all the same. That means the mean is the same as all of the data values. So let's look at another example here. So example 5, consider the following data sets which all have the same mean. So they all have the same mean, and you can see that that is, actually we'll draw it straight down. Whoopsie, I kind of went off here, didn't I? It's all at 4. Rank the data sets from smallest standard deviation to largest standard deviation. And remember, standard deviation is the deviation from the mean. Okay. At first glance, everybody wants to say this one because they're all even. But it's actually which one has the most number of data values. Remember this over here on the vertical represents the number of data values. So the one with the largest standard deviation is going to be the one that has the most data values away from the center. And this one here in the middle is that it has most of its data points away from the center. So this is the largest. This one is the smallest. Most of its data points are at the center, right? And then it dwindles off. So variance and standard deviation is a concept that takes a while to kind of really think about and contemplate. So don't feel like you should understand completely right off the bat today. Let's go ahead and flip our page. We're going to go back to talking about how data points could be unusual and could be 2 standard deviation above the mean or 2 standard deviations below the mean. And why do we say that that's unusual? And that's because of the empirical rule. So the empirical rule, if a distribution is roughly symmetric, we call it normal or bell-shaped. Remember, we say that when the mean is similar to the median. And once we say that we have a bell-shaped or symmetric or normal data set, then we can use this rule of thumb. And the rule of thumb says that approximately 68% of the data will fall within 1 standard deviation of the mean. So down here in the picture, you can see that that's 34% could fall below the mean by 1 standard deviation, and 34% could fall above the mean by 1 standard deviation. That's, if you add those two together, we get the 68%. Approximately 95% of the data will lie within 2 standard deviations of the mean, and approximately 99.7% of the data will lie within 3 standard deviations of the mean. If the data set is not roughly bell-shaped, i.e., if it is skewed right, skewed left, or bimodal, then the empirical rule does not apply. Okay, so if we have skewed data, we can't use this empirical rule at all. So you'll see in your yellow sheets that there is a curve, and it's all filled out with the percentages, and then it's kind of just has the symbols at the bottom here. Okay, so it's important that you understand, and you always fill in the percentages, and at the bottom we actually fill in our data values. So it says the x-axis is a horizontal asymptote, symmetric around the mean. The first standard deviation falls at the inflection points. Inflection means where it starts to turn. So if you were to draw a straight line from the mean, the top here, where the mean starts and goes straight down, is where it starts to turn. So you can see it starts to turn right here at the first standard deviation. For problems with the empirical rule, Keep the standard deviation lines vertical and spacing even. Label each section with the appropriate percentage and label the vertical lines with appropriate axis labels. Okay, so 68% of the data will fall within these boundaries. These are boundaries. Once we take the mean and we subtract a standard deviation, that's a boundary on the left. And when we add a standard deviation, it's a boundary on the right. It says anything beyond 2 standard deviations away from the mean is considered unusual. That's going to be our rule that we're going to use. So I usually mark that with the 2 standard deviations out here, and I just mark it for myself and say that's unusual. And then I do the same over here. Okay. So we're going to look at our last example for lesson 3.2. I know we've learned a lot in this lesson. It's a lot to take in. Example 6 says, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the U.S. ages 20 to 29 was 64 inches, with a sample standard deviation of 2.75 inches. Assume that the heights of women in the U.S. are normally distributed, so we can apply the empirical rule. Construct the accurate normal distribution with the parameters and percentages labeled. Parameters are the heights down here. Okay, and percentages labeled. Your shape, your scale, your numbers and percents all matter when drawing. So let's go ahead and draw our mean. And we said the mean was 64 inches. And then at the first inflection point is going to be 34% to the left and 34% to the right. And that's found by taking 64 minus 2.75. 64 minus 2.75, and we get 61.25. And then you can arrow up and hit enter, and then you can go and edit and say, I want to know what 64 plus 2.75 is, and that's going to be 66.75. Okay, so 68% of our data should fall between those. Then the second standard deviation stretches out our data another 13.5% to the left and 13.5% to the right. So if we were to add all of these, that's where we get the 95%. Is within 2 standard deviations. So to get the next value, we can either start from the beginning and subtract 2 of our 2.75s. 64 minus 2 times 2.75. And we get 58.5. Or you could just say 61.25 and subtract a single to go the second one to get to 58.5. So there's 2 options. So here we can say, let's add, and let's find the one up here, which is going to be 69.5. And then our third standard deviation is right here, our third boundary. And if we go by our sheet on the prior page, 2.35% should fall between the second and the third. And that's when I usually have to write them up here because it gets too small. And 2.35% here. And then very last boundary out here is 0.15% and 0.15%. And so if you add these, so if you add 0.15 plus 2.35 plus the ones over here, 2.35 plus 0.15. That's where we get our 5%. So everything outside of here is unusual, and everything outside of here is unusual. Okay, so let's soak it all in and we can go ahead and answer these questions. It says, estimate the percent of women that are between 64 and 69.5 inches tall. So that would be right here to right here. So letter B, we're adding the 34%. I'm gonna clear this out so you can all see. 34% up to the 69.5, which is 13.5% plus 13.5%. So we have 47.5% of women or girls. C says, estimate the percent of women that are taller than 69.5% or 69.5 inches. That would be everybody past 69.5. So 2.35 plus 0.15 is 2.5%. It says, estimate the percent of women that are taller than 64. Well, 64 is at the mean, so that should be 50%. E says, estimate the percent of women that are between 61.25 and 72.25 inches tall. We didn't add that out here. So our third standard deviation was 72.25. And our third standard deviation over here was the 55.75. So we want to know what percent are between 61.25 right here and 72.25. So not the last little bit, but just in between there. So we've got 34 plus 34 plus 13.5 plus 2.35, which comes out to be 83.85%. And lastly, it says, what heights for women would be considered unusual? Think about what would we consider to be, what heights would be considered unusual. So anyone shorter than 58.5 inches, right? We said over here, the second standard deviation. So shorter than 58.5 inches or taller than 69.5 inches. They would be considered unusually tall or short. If you have any questions, please reach out to me. Sometimes you may feel it's beneficial to rewatch a video. If you're struggling or didn't get something, that's the great part, is you can stop these videos and rewind. Go back and relook at them if you have questions or not sure if you got everything. And we'll look forward to seeing you for the next lesson, for lesson 3.3.